Okay, hey, welcome back, class. Today we're going to cover potential energy curves. My objective for y'all today is that y'all can identify the different components of a potential energy curve and interpret the data produced by these curves. In saying that, let's dive into the lesson. As we have stated in past videos, chemical bonds occur when electrons either are shared or given to another atom. The nucleus of one atom is what attracts the valence electrons of another atom. This is mainly because the charge differentiation between the positively charged nucleus and the negatively charged electrons. As Coulomb's law states, the distance also plays a role in the attraction or repulsion of these charges. So the further away they are from each other, the weaker the attractive or repulsive forces are between them. Potential energy is considered the energy of an object's position. With atoms, we measure the potential energy or the position by determining the center of the nuclei. So when we are comparing the distance between two atoms, we are measuring from the center of the nuclei of each atom, not the edges of the electron cloud. Atoms contain both kinetic and potential energy at the same time, so their total energy can be found by just adding our kinetic plus our potential energy together. The relationship between the electrons within an atom's kinetic energy and the potential energy is K, or kinetic energy, equals negative 0.5 V, or potential energy. This means the chemical bonds formed is an exothermic process, and a decrease in potential energy is accompanied by the increase in kinetic energy, of which is only half the magnitude of the potential energy. The potential energy surface of an atom within a compound is dependent on the distance between the nuclei from each atom. When two atoms are within a certain distance of each other, the valence electrons from one atom and the nuclei of another atom will start to react with one another and create attractive forces. As atoms come closer together, the distance decreases, and the attractive forces between the two atoms will become repulsive ones, originating from the two nuclei. We can graph the attractive and repulsive forces within a chemical bond by using a potential energy curve. These curves are very useful in defining certain properties of chemical bonds. The internuclear distance in which potential energy minimally occurs is defined by the bond length. This is where the attractive forces start to occur. We identify this point as the equilibrium bond length, and the stronger the bond, the shorter the bond length will be. So the closer to the y-axis, the bottom of the point of the potential energy curve is, the shorter the bond length, and thus the stronger the bond is. Okay, when looking at a curve, the y-axis is going to be labeled the energy within the system, and the x-axis is going to be the distance between both nuclei of the atoms. Finally, if we were going to take the equilibrium bond length or point at the bottom of the curve and extend that point out in either direction, the energy difference between the extended line and the origin of the x-axis is going to be our bond energy. Notice, as we approach the optimal bond length, the energy stored within the chemical bond increases. Once the atoms reach this point, though, if we get any closer together, the energy quickly changes from attractive to repulsive energy. So, if we want to make a graph of the potential energy within a bond of two hydrogen atoms, as the atoms get closer together, we'll see that the bond energy stored within them increases until we have the optimal distance from each other. Once these atoms try to get closer to one another, we see that the nuclei start to repulse each other. Okay, so I believe this is enough for today. Remember, this is just a representation of how potential energy exhibits itself within a chemical bond. Keep up the good work in the classroom, and see you next time.